All right, welcome back to the deep dive. Today, you gave us a stack of sources that take us right up to the absolute speed limit of the universe.
And then asks what happens if we just break it.
Exactly.
That's
Fun one. Our mission today is to get our heads around a purely conceptual, a purely hypothetical thing that if it were real, would just shatter everything we think we know about space and time.
We're talking about the tachyon.
The tachyon.
Yeah. It's a theoretical particle that, according to the math in these sources, would always move faster than the speed of light, what we call k.
So it's not just that it can go faster than light, it's that it must.
It has no choice. It's stuck in the superluminal world.
And right away, that forces us to ask this really foundational question that kind of sets the stage for this whole thing. If something travels faster than light, does it arrive before it leaves?
I mean, that's the core of the problem, isn't it? We're talking about violating the very fabric of time. To understand why it's so disruptive, we have to first look at the mechanics, the really weird physics that would even allow it to exist, hypothetically.
Okay, let's do that. Let's unpack the physics here. You said the tachyon is always moving faster than light. So it's like it starts the race already ahead of a photon and just stays there forever.
That's a great way to put it. Normal matter, everything we are is always trying to catch up to the speed of light but can never quite get there.
Right.
Tachyons are the opposite. They can never drop down to the speed of light.
But wait, why? I mean, a car can slow down. Any normal particle can slow down.
Yeah.
Why is the tachyon different? Why can't it just put on the brakes?
Because its entire relationship with energy is completely, and I mean completely, inverted compared to anything we know.
Inverted.
Yeah, and it all comes from this really bizarre mathematical requirement. It would have to have what we call imaginary mass.
Imaginary mass. Okay, that sounds like something straight out of science fiction. What does that even mean?
Well, the equations from special relativity, they link energy and mass and momentum, right?
Okay.
When physicists play with those equations to see what a faster-than-light particle would look like, the math only works if the particle's mass squared is a negative number.
A negative mass squared.
Yeah.
So the mass itself would have to be an imaginary number.
Precisely. Now, physically, we have no idea what that means, but mathematically, it dictates this just absurd relationship with energy.
Okay, let's break that down. For normal matter, like me, if I want to speed up, I get heavier.
Right.
My relativistic mass increases.
Right. And you'd need more and more energy to go faster and faster until you'd need an infinite amount of energy to actually hit the speed of light.
Which is impossible, so you can't get there.
Exactly.
Okay, so now flip it. What happens to the tachyon, this imaginary mass thing, if it tries to slow down?
If a tachyon, which is already moving above c, tries to decelerate and approach the speed of light from the other side, the math says it would need an infinite amount of energy to do it.
Wait, hold on. So normal matter needs infinite energy to speed up to c, but a tachyon needs infinite energy just to slow down to c.
It's a perfect, beautiful, inverse relationship. That dynamic means the tachyon is essentially trapped. It's trapped in its faster-than-light state forever because it can't possibly generate the infinite energy needed to slow down.
So speed isn't a choice. It's just a fundamental requirement of what it is.
Yeah.
That's the big aha moment right there.
It is, but now we have to move on from the weird mechanics to the, let's call it the catastrophic implication.
Right. This is where we leave the world of weird physics and get into the really big problem, time itself.
This is the causality killer.
And it's the real reason, I think, that most scientists are so suspicious of the whole idea.
Oh, absolutely. Because if tachyons were real, they would fundamentally they'd shatter the law of causality. It's the cornerstone of how we think the universe works.
We all kind of get causality, right? Cause always comes before effect. They drop a glass, then it breaks.
Yeah.
Not the other way around.
Yeah.
But how does going faster than light actually break that?
It ties directly back to Einstein's special relativity. Because time and space are relative to an observer, if you have a signal moving faster than light, there will always be some observers for whom that signal looks like it's moving backward in time.
Ah, okay. So it's not that the particle is always time traveling for everyone. It's that because it's going so fast, you can always find a point of view, a reference frame, where the effect happens before the cause.
Exactly. For observer A, the tachyon leaves point X and arrives at point Y simple. But for observer B, who's flying past in a spaceship really fast, they might see the tachyon arrive at point Y before they see it leave point X.
Time is literally flipped for them.
For them it has.
Which means we could send messages into the past.
Theoretically, yes.
And your sources have this great simple example of this, the flat tire.
Yes, the classic paradox. So Imagine you get a flat tire on your way to work. It makes you super late.
Right. It ruins my day.
So you grab your tachyon transmitter and you send a warning signal back in time 1 hour to your past self.
So my past self getting the warning happens before the cause, which is me sending it.
Exactly. So your past self gets the message, avoids that road, and doesn't get a flat tire. No delay.
Great. Problem solved.
But is it? Because if you never got the flat tire, then you never had a reason to send the warning message in the first place.
And if I don't send the warning, then I do get the flat tire, which means I do send the warning and wonder, oh, that's a loop.
Yeah.
It's a paradox that just breaks logic.
And that is why physicists draw a very hard line. Causality gives us the arrow of time. It gives reality its stability. If the math for tachyons allows for this kind of paradox, then the conclusion is usually that tachyons have to stay in the realm of math, not physical reality.
But hang on. If the math works, couldn't there be some other law, something we don't know about yet, that prevents the paradox? Maybe FTL travel is possible, but nature just stops you from sending a message that would change the past.
That's a great question, and it's something physicists have considered. There are these ideas, sometimes they're jokingly called chronology protection conjectures, where the universe itself would conspire to prevent these paradoxes.
Yeah.
But for now, that's just speculation. Tachyons are a direct challenge to relativity, and relativity is a system that we know works incredibly well for, well, everything else.
So we go with the theory that doesn't break all of reality. That makes sense.
It seems like the safer bet.
Which brings us to our final segment, the reality check.
Right. And the first check is the simplest one. Tachyons are purely hypothetical. No one has ever seen one, detected one, or captured one in any experiment, ever.
They're ghosts in the machine.
Pretty much. And the main objection standing in their way is, as we said, the huge success of relativity.
Why is relativity so dead set against them?
Because relativity is built on one core idea, that the laws of physics are the same for everyone, no matter how they're moving. And the speed of light is the one universal constant that holds all of that together.
It's the cosmic rule that makes everything else work.
Exactly. If you let particles go faster than that, you break the consistency. You let events appear in different orders for different people, and the whole structure of the universe, as we understand it, starts to crumble.
So the tachyon isn't just some quirky fast particle. Its existence would mean relativity is fundamentally flawed at its upper limit.
It's a direct conflict, however, and this is where it gets really strange. The sources do point out that in the deepest parts of theoretical physics, tachyons sort of pop up again.
How?
Not as actual particles flying around, but as features of quantum fields that might help explain some of the biggest cosmic mysteries we have.
Okay, this is really interesting. So even if they don't exist as objects, the concept might be useful. Where could they fit?
Well, two big places come to mind: dark energy and the quantum vacuum.
Let's start with dark energy. We know it's the stuff that's making the universe expand faster and faster.
Yeah.
How could a tachyon possibly be involved there?
Well, dark energy needs to have this weird property called negative pressure. It's like anti-gravity. It pushes things apart. Some very advanced theories suggest that this could be described by a type of fundamental field, a tachyonic field, that has those exact mathematical properties.
So it's not a particle. It's a field spread out across space
Right.
that just happens to have the same mathematical signature as a tachyon.
You got it. The field itself is unstable, and its energy could be what's driving the cosmic acceleration. It's a way to use the weird math of tachyons without having to worry about sending yourself messages about flat tires.
That's a clever way to keep the math, but ditch the paradox. Okay, what about the quantum vacuum?
The quantum vacuum isn't empty space. It's seething with virtual particles popping in and out of existence. It's chaos. Tachyons could represent deep instabilities in that vacuum, like a phase transition.
An instability that leads to something real.
Potentially, yes. Think of it like this. If a field is in an unstable state, it wants to fall to a more stable, lower energy state. That initial unstable state is sometimes described mathematically by tachyonic solutions.
So the tachyon isn't the final product. It's just the marker for an unstable situation that's about to change.
Precisely. It turns the tachyon from a time-traveling spaceship into the mathematical signature of a vacuum that's about to sort of boil over and create something new and stable.
And this brings me back to something the sources really stressed. When you get this deep into physics, into particles appearing from nothing or superluminal fields, our everyday logic just completely breaks down.
It does. Our intuition about how things should work is useless here. You have to rely entirely on the math and on your imagination, even when it leads you to absurd-sounding places, like needing infinite energy to slow down.
It really feels like the universe is only obligated to make sense mathematically, not necessarily to a person.
That's the lesson of quantum mechanics in a nutshell. It works, it's predictive, but it couldn't care less about our common sense.
That's a great place to pull it all together. So to recap for everyone, we've had this deep dive into the tachyon.
And we landed on three key takeaways. First, if it's real, it's forced to be faster than light because of its strange inverse relationship with energy.
Right. Second, slowing it down to the speed of light is impossible. It would take infinite energy.
And third, the big one, its existence would destroy causality, allowing for time paradoxes.
But finally, even though it probably can't exist as a particle, the idea of the tachyon, its mathematics, is still alive and well, helping physicists model some of the deepest mysteries in the cosmos, like dark energy.
And that realization that at this level, only imagination and mathematics are reliable guides, that's so important.
So here's the final thought for you to chew on. If the mere existence of a theoretical particle forces us to question the rules of cause and effect, probably the most basic rule we live by, what other foundational rules of reality, things that seem totally unchangeable to us right now, are just mathematical ideas waiting to be challenged?
What rules do you take for granted every single day?
Until the next deep dive, thanks for joining us.